My name is Allison Bateman, and today we're going to be talking about our feedback project, which involved designing a driverless car. Alright, so one of the problems that we realize in this nation is that there's 49.5 million disabled people in this country, and around 13% of those actually have trouble getting transported around, so they always have to have an assistant with them. So we want to appease that situation and try to make it as easy as possible for them to be independent on their own. So we think that making this automated vehicle would be really helpful to them so they can get to work alone, or they can go to different houses and they would never need to have this assistant with them. So our goal is to basically simulate this system for our car, where it's taking the force that the car is putting onto the road, basically, as our input, and then our output would be the position, which we later relate to velocity. So basically this control system, designing this as a control system, allows the input to be constantly taken into consideration along with the output. So say the car is moving too fast onto the highway, we can take that as a design constraint, and the force of the car would then decrease so that the speed would also decrease. We think this would be helpful because then it can kind of work along with the distance on the highway and adjust for different speed limits on the road, since they're not all the same speed limit. So one of our main control goals, as I stated before, was being able to merge onto about highway speed, maybe even going a little bit faster. And so the model of the car, obviously, it has to start from rest, because you're not just going to be jumping into a moving car, and it has to accelerate into the flow of traffic as well. So as if it were on a highway on-ramp, because we don't want it going too slow or too fast. We also want that relatively quick acceleration onto its peak velocity, but we don't want it to completely overshoot this velocity because we don't want someone to be in the car and completely out of control about what speed they're going at. So next, Charles is going to be talking about some of our model iterations.
Hi. So to begin our modeling, we took our vehicle and used an impedance network to model it. We ran it through a couple iterations. First iteration, we assumed mass of the vehicle to be 1,000 kilograms, a drag coefficient of 200, and an engine force of only 2,000 newtons. We ran this through an iteration, and we found that the rise time, basically the time to get up to 60 miles an hour, was just way too slow. It was unsafe and not practical for a car accelerating onto a highway. So what we had to do, we had to go back, make another iteration, change some of the values. So what we did, we cut some weight of the car down to 800 kilograms. We made it more aerodynamic, which dropped the drag coefficient to 100, and we increased the power of the engine up to 3,500 newtons. We ran this through an iteration, and it was able to give us our, these design parameters was able to give us our desired rise time. But to model the system, we used a transfer function modeling the output position over the input force, multiplied both sides by s in the frequency domain to convert that position to a velocity, which is our output goal. And we ended up with a plant G of s of 3,500 over 100 plus 800s. And to describe the analysis on this and more in-depth talk about the rise time several times will be Marcello.
So after taking that plan, we plotted the step response, and we found that the vehicle was able to reach a maximum velocity of around 78 miles per hour, which is reasonable. And it reaches our 0 to 60 goal in about 11.5 seconds, which is reasonable given other current models on the market. If you look at a 2012 Toyota Prius, its pickup speed from 0 to 60 is roughly 10 seconds. So we're doing pretty good there. After this passed the verification stage of, okay, this plant is going to work for what we want to do, we looked to make sure that this plant was stable. And it turns out this only has one open loop pole, and it's in the negative 1/8, which is in the left half plane, making it stable. In addition to this, we ran a Ralph Horowitz Bimbo stability in order to determine what area of gain we would be able to use. And we were able to determine that any gain above negative 100 over 3,500 would be acceptable. After running through some calculations to determine the best gain possible to achieve our rise time, we determined that a gain of 0.0285 would be acceptable for our model. So the next step was figuring out which controller would be best for our application, and we determined that a proportional controller would be the best. One, because it's extremely simple. There's no integrator or derivative portion of this, which means fewer parts that could break in the overall project. So that was a huge plus for us. In addition to this, we didn't need an integrator, just because this is a first order system, where, as you saw on the previous slide, it has that turkey in the oven shape and it's leveling out. There's no overshoot that we need to correct or error that's really going to get out of control. So our final analysis gave us that we had a rise time of 17.5 seconds, and there is 0% overshoot, again, because it's that first order system. You're not seeing it shoot over and then settle back down. Ultimately, this ended up giving us a steady state error of 0.03, and that is a result of disturbance. So if a disturbance is given onto our plant, this proportional controller will help correct that and bring the error down to this value. Next is Lauren to talk about things.
I'm going to talk about the verification of our function. So as Marcello said, our rise time was 17.5 seconds, and when we ran our function through the MATLAB Simulink, the results were these 4 graphs on the right. So in the bottom right is the step response, and it's marked by the rise time is marked by the small blue dot over there. But in both our results and the Simulink, it was 17.5 seconds, which means though the scale of that graph is smaller than one of ours, the results are the same. So for the percent overshoot, it was 0%, which gives us a zeta value of approximately 0.9, which corresponds to a phase margin on this bottom left graph of 90, which also verifies our results. The steady state error was 0.031, which corresponds to the top left graph over here. And this is the bogey plot, which simply means that there was not a large error between the function and our results. And all of this was based on a k-value of 0.0285, which was our estimate at the beginning, and was multiplied by our g function to give you. So, based on our design, our analysis, and our verification, this is what we believe to be the best choice for our design for our driverless car. Thank you.